Hello, everyone, and welcome to our first video on Unit 3.2, where we're going to be talking about exponential functions. I know it seems like kind of a big jump, like a big left turn since we were talking about inverse functions, but I promise it will make sense once we get to Unit 3.3. But when we're talking about exponential functions, I just want to do a quick review of exponent rules because it never hurts to go over these ones, especially since these will become like they're already very, very useful, but they'll be especially useful in calculus if you plan on taking 181. So the first one we've got is that if you have two functions with or two things with the same base, so x to the a and x to the b, then you just add the exponents. So that is to say, for this example, x to the third times x to the seventh, that would be x to the, I wanted to use black pen, that would be x to the 3 plus 7 or x to the 10th. Next one, if you have x to the a raised to the b, so if you have a power raised to a power, then you multiply the powers. So x to the sixth raised to the third would become x to the 18th. This would be x to the 6 times 3 or 18. Then one that a lot of people get confused is this one versus, and so you don't need to, please don't write this down, versus x plus y to the a. Notice the big difference here. The big difference is that this one is a sum where this is a product. So this does not break down the same way. It doesn't become x to the a plus y to the a. So, but if you have a product of two things, x to the a x times y to the a, then each thing gets raised to that separate power. So, for example, if we have x y squared raised to the fourth, that'll be x to the fourth, and then it'll be y to the eighth because it's going to be y squared raised to the fourth. So it's going to be a combination of this property and this property. And then one of the most useful, or another one that's useful, is one to any number, whether it be an irrational number, a fraction, whatever it may be. One to any power is one. So one to the 6,123, still just one. Then if you have two things with the same base and different exponents being divided, you take the difference of the exponents, a minus b. So in this one, that would be x to the 3 minus 12. That would be x to the negative 9. And I'm going to write this as or 1 over x to the 9, because that's actually going to be one of the properties right below, is that if you have a negative exponent, you can rewrite it. It's the same thing as writing it as 1 over x to the a. So x to the negative 7, that's the same thing as 1 over x to the 7th. I know these might seem silly, like unnecessary for now. I promise you, this property gets used so often in calculus, you'd be surprised. And remember, these are all equal signs, so this is true backwards and forwards. We can break down x to the 10th into these two pieces. You can break down x to the 18th into an x to the 6th times an x to the 3rd. Or, I mean, as an aside, you could also do x to the 3rd raised to the 6th. It doesn't really matter. So just remember that these are equal signs, so it's true in the forward direction and in the backwards direction. Next one is if you have, much like the x times y to the a is x to the a, y to the a. If you have x divided by y, all being raised to the a, that's x to the a over, oh, that's a typo. Can't believe I missed that. I'll fix that when you guys get to see the thing. But anyways, so this would become x to the sixth over y to the negative fourth, because it would be 3 times 2, that's 6, and then negative 2 times 2, that's negative 4. So we could leave it like that, or if we wanted to, we could write it or x to the sixth, y to the fourth, however we want to. And then any number raised to 0 is equal to 1, except for 0 to the 0, which is what we call indeterminate. But more on that in a different course. But any number that we're usually used to seeing raised to the 0th power is equal to 1. So that is to say, this is going to equal 1. Negative 19 to the 0 is 1. Now, it's not going to be, like, it's a very, very useful property regardless of where we are. This way to convert between exponential form and radical form. X to the n over m is equal to the mth root of x to the n. So for example, this will be the square root, because this like it's going to be the second root. So, and the second root is the square root. So this will be the square root of x to the fifth. Now, a good way to remember this is this following mnemonic. It's the powers above powers above and roots below, quote unquote. So imagine the power goes above and the root goes below. So if you're going from one way or the other, you can utilize that fact. So like the mnemonic device is like, the old saying of the powers above us, right? Whether you believe in God or not, but like regardless, the powers above us, whatever it may be, and then roots grow below us. Trees' roots grow below us. So that's a nice little nifty remembering trick. This will be used a lot in calculus, and we'll use it a little bit here too. So anyways, we'll start up now that we've gone over a little bit of exponent rules, we'll start talking about exponential functions. So definition, an exponential function is of course a function, but it's a function of the form or f of x, depending on your situation, is equal to b raised to the x. Some textbooks will say a to the x, some will use a different letter, but b to the x. I think that makes the most sense because then you can call b the base of the exponential function. So there's this added stipulation, though, where b must be strictly greater than 0 and b cannot equal 1. And so I want to explain why we write that requirement. Reason for b must be greater than 0. Say b was equal to -4. If b equaled -4, then y would equal -4 raised to the x, and y of 1/2 would equal -4 to the 1/2. But utilizing this property above, power goes above and root goes below. So this would be the square root of -4 to the first power, the square root of -4, which does not exist. So the key thing is that we can't have negative bases because that ends up causing a lot of problems with all the fractions and stuff. Integers, it'll be fine with. -4 squared is +16. -4 cubed is -64, and so on and so forth. It's fine with the integers, but it's once we start working with radicals, especially even radicals, that things become problematic. So anyways, and b can't equal 1 because if you've got b equal to 1, then you've just got y equals 1 to the x, but we realize that that would just be 1. So anyways, let's go ahead and look at the graphs of these two functions, these two exponential functions. The first one, f of x, has a base of 2, and g of x has a base of 1/2. So I've already computed the first row of this for us. So f of -2 would be 2 to the -2, and then utilizing this property up here, that's the same thing as 1 over 2 squared, which is 1/4. So f of x has the point -2 comma 1/4. Then you'll also get 2 to the -1, which is 1/2. So we have the point -1 comma 1/2. 0, you'd get 2 to the 0, which we just saw is equal to 1. So we have the point 0 comma 1. 1 is 2 to the first power, which is just 2. So that's going to be 1 comma 2. And that plugging in 2 for x, you'll get 2 squared, which is 4. So we have 1 comma or 2 comma 4. And I'll make both charts before plotting everything. So the next one, this is kind of a little bit more algebra heavy, but so g of -2 would be 1/2 to the -2, which is the same thing as 1 over 1/2 to the 2 to the second power. And then that's going to be 1/4, but you're dividing by a fraction, so you'll flip and multiply, thereby getting you 4. So the point -2 comma 4 is on this graph. Plugging in -1, we'll get 1/2 to the -1, which will be 2. And so we have the point -1 comma 2. Plugging in 0, 1/2 to the 0 is equal to 1, because any number raised to the 0 is 1, save for 0 to the 0, but we don't need to worry about that. 0 comma 1. And then you'll get 1/2 raised to the first power, which is just 1/2. So we have 1 comma 1/2. And last but not least, we'll have 1/2 squared, which is 1/4. So we have the point 2 comma 1/4. It's quite interesting that the x coordinates, the y coordinates flip with those things. And so let's go ahead and graph them. I'm going to graph the first one in blue and the second one in purple. And so plotting the first one, so 2 to the x. So we had the point negative 2 comma 1 fourth. That's roughly there. Negative 1 comma 1 half, 0 comma 1, 1 comma 2, and 2 comma 4. And so filling out that graph, what that's going to end up looking like, if you were to keep going, you'll see you'll get 1/8, then 1/16, and then 1/32, and so on and so forth. Meanwhile, it'll get it looking like that. So that's going to be f of x. And g of x, you had negative 2 comma 4, negative 1 comma 2, 0 comma 1, so the same point. Interesting that they both have that point. 1 comma 1 half and 2 comma 1 fourth, like that. And so this graph looks like a reflection across the y-axis. I wonder why that is. Let's think about it. We'll get to it in just a little bit, but those are the graphs of them. So one thing that you can notice right away is that these things are never, ever zero. Give me 1 second. All right. So now we're going to get some actual properties about exponential functions. So these are the useful things to know about them. Properties. So the domain, as we can see above, the domain will be all real numbers. So negative infinity to positive infinity. And that makes sense. If you plug in any number into an exponent, it'll give you a number back. Um, the range, however, is parenthesis 0 to positive infinity. So this is an important fact about this. So since the range is equal to 0 to positive infinity, this means this means b to the x is strictly greater than 0 for all x. Any exponential function will always be positive, and therefore b to the x is never equal to 0. This will play a role in many places. I believe we'll probably end up using this fact at some point in Unit 3.5, I believe. But this is also very, very useful in calculus when trying to find critical values and things like that. But we'll get there when we get there, right? That's a few courses away. We don't need to worry about that. But just suffice it to say, a very important fact about exponential functions is that they are always positive, meaning that they're never negative and they're never zero. Then you've got some important points. Every exponential function has the point 0, comma 1. Every basic exponential function of the form y equals b to the x. Um, and then f of 1 would be b to the first power, which would be b. And f of negative 1 would be b to the negative 1, which is 1 over b. So we have the important points 0, comma 1, 1, comma b, and negative 1, comma 1 over b. These are used for transformations. Yay! We all love transformations. That was our favorite section, right? We can even put a smiley face to say that we love it. This is our favorite thing, right? I'm of course being facetious. I know that's uh, one of the sections that students tend to like the least, but whatever. I like it a lot. Oh, interesting. I'm gonna have to fix that too. These points were got all messed up. So your worksheet will be fine. I'll fix that in just a moment. Like it never happened. We'll get to that in just a second. But I know some of you may not be pleased about that, but the good news is you can also just use your calculator to find points, which we'll talk about in just a moment. And then the other property that exponential functions have is they have a horizontal asymptote at y equals 0. And that kind of is further confirmed by the range, right? The range is 0 to positive infinity, meaning that it never equals 0, but it gets closer and closer. When we plugged in negative 2, we got 1/4. If you plug in negative 3, you'll get 1/8, then 1/16, then 1/32, and so on and so forth. You're getting closer and closer and closer to 0 as you get further and further down on that in those x values. And then the graph of b will vary based on the value of b. If b is larger than 1, then the graph will go up like this. It'll start down in the bottom left and increase in the top right. So this function is always increasing. And the secondary situation would be if is between 0 and 1. So like 1/2, 1/3, 2/5, something like that. And the graph will end up looking like this. It'll have the point 0, comma 1 and 1, comma b, but this case b is less than 1, so that's why it's going down. And so this is always decreasing. So now there's one special case though, which is called the natural base. So the natural base is a number e, and it's written as e, just like pi is a number, but we write it with a symbol pi. E is another number that we've written with the symbol E after, and it's named after its creator, Leonhard Euler. I know it looks like Euler, but it's actually his last name's pronounced Euler. Very, very, very famous mathematician, and he created this number, and it's approximately 2.71828, but it goes on forever, just like pi does, right? An approximation for pi would be 3.1415. 2.7182 is a good enough approximation for E. But the key thing is that E is just a number like anything else, like any other number. I'm going to actually highlight this. So where does it come from? That might be a good question to ask. And the simple answer is that it comes from calculus. In particular, one of the aspects you'll learn in calculus is talking about limits at infinity. And this quantity, so 1 plus 1 over n raised to the n, as n goes to infinity, that will go to e. I encourage you, if you're bored this weekend, plug in like 1,000 for n. So 1 plus 1 over 1,000 raised to the 1,000, and you'll see you'll get a number relatively close to 2.718. So the key thing is, so E is just a number, and y to the ex is an exponential function like any other function, just like any other. And so the last thing for this video is just kind of looking at them visually and noticing some patterns. So the orange curve is y equals 10 to the x. The green curve is y to the equals 5 to the x. The red curve is y equals 2 to the x. And the blue curve is e to the x. So what you'll start noticing is that the bigger the base, the more steep the graph. So that's the key point here, is that the larger the base, the steeper the graph. So, and you can see that E is about 2.718, and that's why it's between 5 to the x and 2 to the x. It's larger, like its base is larger than 2, but closer to 2 than it is to 5. And I know it's kind of hard to see, but it should, like, and I didn't graph these things perfectly, but it should be a little bit, oh, and that's also a little typo, that the green arrow of y equals 5 to the x got hidden behind. I had to make a few movements either way. It'll be fixed when you guys get to see it. There's the green arrow. It's hidden behind the orange one. Oh well. But you'll see that it's in between those two because its base number is in between the two. And that'll do it for this one, and I'll see you guys on the next one.